Okay, we're going to start on equilibrium and liquid vapor systems. First, we're going to review vapor pressure. We've talked generally about vapor pressure. We're going to look at it in more detail and using some of the kinetics that we've just learned. So, at any temperature, there are going to be some molecules in the liquid that have enough energy to escape. And this really comes about from the energy distribution of a sample of matter. If you remember the Maxwell-Boltzmann curve, we've got kinetic energy and we have the fraction of molecules at any given kinetic energy or velocity. And the blue line represents a sample of matter at a low temperature, and the red is the same sample of matter at a higher temperature. Similar to the minimum activation energy, when we're talking about a sample of liquid and a vapor, there is a minimum amount of kinetic energy that is needed for that molecule to escape or to have enough kinetic energy to overcome the intermolecular forces of that liquid. And hopefully you can see and familiar with the Maxwell-Boltzmann curve that this red part here, these are the greater number of molecules at a higher temperature that possess a kinetic energy greater than that minimum needed to escape into the vapor phase. So as the temperature rises, we get more and more molecules that have enough energy to escape. They have enough kinetic energy to overcome those intermolecular forces. Now, when more of those particles escape, I'm going to have more particles up here in the vapor phase or in the vapor space of my container. And in this example, we have some liquid ethanol in the liquid form in a closed spherical container hooked up to a manometer tube. With where the level is here, you can hopefully see that the atmospheric pressure is equal to the pressure inside my vessel. As I heat up my liquid ethanol, I increase the number of particles that have enough kinetic energy to escape into the vapor phase, and my gas pressure is going to increase, okay, as those particles escape. And you can see the pressure being greater than the atmospheric pressure. Now, thing to note, at the same time that these particles have enough energy to escape, you would also have to look at the particles in the vapor phase. Some of those particles are going to fall below the energy needed to stay in the vapor phase, and if they happen to connect with the surface of the liquid, they're going to get pulled back into the liquid phase. So when I have this closed container at any given temperature, the particles moving into the gas phase are going to eventually equal the particles in the gas phase that lose some kinetic energy to other particles, and they're going to fall back into the liquid phase. And I'm going to set up what's known as a dynamic equilibrium between that liquid and the vapor phase. So while those liquid molecules are evaporating, vapor molecules are condensing, and at equilibrium, those two processes happen at the same rate. Let me erase. Okay. So what we find is the definition of a boiling point is the boiling point of a liquid is the temperature at which its vapor pressure is equal to the atmospheric pressure. Okay. The normal boiling point is the temperature at which the vapor pressure is 760 torr, which is standard pressure, 1 atmosphere. And what you'll see is these vapor pressure temperature curves for different substances. If you remember before when we were talking about Dalton's law, that the vapor pressure of water is only dependent on the temperature, it is because of that Boltzmann's curve and the number of particles that can escape from the liquid to the vapor phase depending on the pressure. Right. We're going to pause here and watch a movie. I just have to go locate it, so we'll be back in just a sec.
A liquid confined to a cylinder, as shown here, with no other substances present, exerts a vapor pressure in the space above it. Molecules continuously transfer back and forth between the gas and liquid phases. The gas pressure in the cylinder represents the vapor pressure of the liquid that results from this equilibrium. As the temperature of the cylinder increases, the average kinetic energy of the molecules increases in both the liquid and gas phases. A higher average kinetic energy facilitates the escape of molecules from the liquid phase into the gas phase. At the same time, the rate of return of gas phase molecules to the liquid also increases. A new equilibrium point is reached at a higher gaseous vapor pressure. The increase in vapor pressure with temperature is exponential. In this equation, A and B are constants that differ from one liquid to another. The absolute temperature is expressed in kelvins. When we take the natural log of both sides, we obtain this equation. It tells us that a graph of log vapor pressure versus the reciprocal of the absolute temperature should be a straight line.
Okay, so when we talk about phases, it also helps to talk about a phase diagram. A phase diagram is a diagram that shows the different phases of a substance at a given temperature and pressure. Temperature is on the x-axis, pressure is on the y-axis. At any given combination of temperature and pressure, you can use a phase diagram for that substance to determine what phase that diagram is in, or that substance is in. It also gives you when you will have equilibrium between, say, the gas phase and the liquid phase. It would be all along this border. Equilibrium between the solid and liquid would be along this border. And then the sublimation and deposition. Okay. There is a triple point, which is equilibrium of all three phases. And there is also something called the critical point. And above this critical point, your substance is in something called a supercritical fluid. We're going to watch a short video at this point, and it should explain.
A phase diagram indicates the temperature and pressure conditions under which a substance is a solid, a liquid, or a gas. The lines that separate the phases are called phase boundaries. At any point along a phase boundary, the phases exist in equilibrium with one another. For example, in the phase diagram of water, at 1 atmosphere of pressure and 100 degrees Celsius, liquid water and water vapor exist in equilibrium. This point is known as the normal boiling point of water. Likewise, the temperature at which solid and liquid water are in equilibrium at 1 atmosphere of pressure is known as the normal melting point. The point at which all three phase boundaries come together is known as the triple point. This corresponds to the temperature and pressure combination at which all three phases of a substance exist simultaneously in equilibrium. When a sample of solid water or ice at 1 atmosphere of pressure is heated, it will melt when the normal melting point, 0 degrees Celsius, is reached. At this point, water crosses the solid-liquid phase boundary. If the sample is heated further, the liquid water's temperature will increase until it reaches the normal boiling point, 100 degrees Celsius. It will then vaporize, crossing the liquid-gas phase boundary. Once the liquid is all vaporized, the temperature of the water vapor will increase as more heat is added. If a sample of solid water is heated at a pressure below the tribble point, it will sublime rather than melt as the temperature increases, because the only phase boundary it will cross is that between the solid and vapor phases. We can also track the changes in a sample of water as we vary pressure. If the pressure is increased on a sample of water vapor at 110 degrees Celsius, it will condense as it crosses the gas-liquid phase boundary. Note that a sample of solid water or ice at a temperature slightly below the normal melting point will cross the solid-liquid phase boundary and melt as pressure is increased. This is one of water's unusual properties. The critical temperature is the temperature above which a gas cannot be liquefied regardless of the amount of pressure applied. The critical pressure is the pressure necessary to liquefy a gas at the critical temperature. The critical point is defined by the critical temperature and the critical pressure. Note that there is no phase boundary beyond the critical point. A substance in this region is known as a supercritical fluid and has properties associated with both gases and liquids.